Hi guys, Mr. Kane here.
Hi guys, Mrs. Goswish. There's something wrong.
There's something very wrong. You know what? Let's not say what it is. That'll be the homework tonight.
There
Tell
you
us
go.
what's wrong.
What's wrong with this picture? What
All
is
right.
wrong?
What's wrong with this picture?
Something feels funny.
Something does feel funny. Empirical formula.
All right.
By definition. So today's about empirical formula, guys. So by definition, empirical formula is the smallest whole number ratio of atoms in a compound.
Do you know I call this EF for short because I'm such a lazy person?
It sounds good.
Yeah. That sound nice?
It does sound nice. So, Mrs. G, is this an empirical formula?
Nope. No, it is not the smallest whole number ratio of atoms. I can reduce that down.
Oh, yeah, the 2 and the 6. They're both divisible by 2.
Correct.
So we could actually reduce those subscripts to CH3.
That's an empirical formula.
This would be our empirical formula here. Right down there, CH3.
Okay.
Now, that's pretty easy to do if you already know what the formula is.
Yes, yes.
Unfortunately, in Dalton's time, they didn't know, and they were trying to come up with empirical formulas of compounds.
Oh.
So they went to their labs, and they had to actually do steps to figure out the empirical formula of things.
Okay.
Eventually, you can get the molecular formula, the real formula. But basically, if you want to determine the empirical formula of something, you have to take the compound, and you have to find out what the mass of each element is in the sample. So you have to decompose it into its constituent elements.
Okay.
And then you can actually do these 4 steps and figure it out.
So if I have a compound with carbon, hydrogen, and oxygen, I need to find the mass of the carbon, the mass of the hydrogen, and the mass of the oxygen. That's the first step, correct?
That's right, yeah. Mm-hmm.
Mass in grams, right?
Mass in grams, right.
Okay.
Now, most of our problems, guys, aren't going to be done in the lab. You're not going to actually be doing any decomposing. But what you will be doing is you'll be taking data. You'll be taking word problems, and you'll be doing this. Sometimes the information is going to be given to you as percentages. So if you're given percentages, all we have to do is assume that the sample is 100 grams. That way the percentages are going to be equal to the masses. So for instance, if you have that carbon, hydrogen, and oxygen compound, and it says 53% of it is carbon,
and that's 53 grams.
If you're assuming 100 grams, yeah.
Oh, that's nice and easy.
So just assume it's 100 grams and change the percent sign to a gram symbol. You don't have to show any work or do anything like that.
So for regular chem, most of this is going to be pencil paper exercises, correct?
Yeah, even for honors chem, this is paper and pencil exercises.
That's true, yeah, even for honors, because it's kind of an elaborate lab to decompose something and catch it all. Okay.
Yeah, it is kind of elaborate, yeah. Step 2, we calculate the moles of each element. So we've been doing mole calculations.
Yeah, this was 2 videos ago. You learned how to change from mass to moles.
Right, so we're going to convert from mass to moles. This gives us a nice molar ratio, but if I tried to write the molar ratio as right now, it's got fractions, it's decimal form. So, you don't have C62.4, H94.3 or anything like that. You don't have that fraction.
When we were doing the other video, we were getting results like 1.43, 4.67 moles. So you're saying you can't use those as subscripts.
Right, you can't use those as subscripts yet because they're not whole numbers.
Yeah, that makes sense.
Okay, so the third step is to divide the moles by the smallest number. This is a mathematical trick. We're going to make these numbers look like they're, we're going to make them look like they're whole numbers almost.
Okay, so let me get this straight. So for number 2, I've changed my mass to moles. So I've got a bunch of moles staring me in the face for all the elements in the compound.
Right, so carbon, hydrogen, oxygen, you've now got 3
different
molar ratios.
Moles. Okay, for number 3, I have to pick the smallest number in number 2 and divide them all by that number?
Yeah, that's right. And so one of them, you're dividing it by itself.
Oh, so I'll always have a 1.
Right, you'll always get a 1.
Okay.
Yeah, and then most of the time you wind up getting numbers that look like fractions that we recognize, 2.53, so that's 2.5.
Okay.
Sometimes you get 0.99, that's 1, right? Or 1.03.
Okay.
Okay, so these numbers have been rounded a couple times. If they look like they're close to a whole number, they're going to be a whole number. If they look close to a fraction like 2.5 or 2.25, they're probably those fractions.
Okay, so there's a 4th step here, isn't there?
There's a 4th step. We still can't have fractions.
Okay.
So when necessary, we're going to multiply these subscripts, these numbers that we've been getting, by 2, 3, or 4 so that we get whole numbers, so that Dalton is happy.
Okay, so in step 3, if I get a 1.01 or a 0.999, I'm good.
Right. You call it 1.
Okay, but if I get a 1.5, a 2.5, a 1.33, or a 2.67, I have to do step 4.
Right. You're going to have to do step 4, and you're going to have to multiply all of them so that you get a whole number.
So the 1.5, the 2.67, and the 1.33 are not close enough to round.
Nope.
So you got to do step 4.
Yep.
Okay.
Let's do an example. We'll make this clear as water.
Okay.
Okay. Oh, before we do the example,
a poem.
A poem.
It's all yours.
Humpty Dumpty sat on a wall. Oh wait, that wasn't the poem either. The poem that we're trying for is percent to mass, mass to mole. Divide by smallest, multiply to whole.
Percent to mass, mass to mole, divide by smallest, multiply till whole. Those are the steps in a nice little poem.
Yeah, those are nice 4 steps. So if you have trouble memorizing those 4 steps, this is easier. All right. The example here, guys, is this. What is the empirical formula for a compound that has a sample of 25.9% nitrogen and 74.1% oxygen?
Okay, so we have a compound that is made only of nitrogen and oxygen.
Mm-hmm.
And if I follow the steps, I will find the correct subscripts for the nitrogen and oxygen in the compound.
Correct. So that when I'm done, I will know what subscripts to put on N and O. Is it N2O1? Is it N102? Is it NO3? What is it?
Okay, so step 1, get the masses of the nitrogen and the oxygen in the compound, which are basically staring me in the face right now, correct?
Correct, because if it's 25.9% nitrogen, if we assume that it's 100 grams of a sample, then 25.9 grams is actually nitrogen. And 74.1 grams of it is oxygen.
Okay.
Okay, so what we're going to do next, that was the first step, percent to mass.
Okay.
Here's the start of the second step, mass to mole. So we are going to do a conversion here.
Right, from mass to mole.
Sit down. So we are going to do a mass to mole conversion. And this is for nitrogen, and this is for oxygen. So it's going to be 14.01 grams for nitrogen for 1 mole, and 1 mole of oxygen is 16.00 grams.
Where'd you get the 14.01 from, Mr. King?
The periodical table.
Oh, okay. And the oxygen, why isn't it 32.00?
Because this is oxygen in a compound, so we're talking about atoms of oxygen, not molecules of oxygen gas.
Okay.
All right. So we're going to get some answers here. Grams are going to cancel with grams. Grams are going to cancel with grams. We'll wind up with moles.
Okay, so 25.9 divided by 14.01 is, with the right number of sig figs, 1.85 moles of nitrogen.
Okay.
And 74.1 divided by the 16, with the correct number of sig figs, is 4.63 moles of oxygen.
All right, so the third step is going to begin right here. We have to divide by the smallest, because I can't say N 1.85, O 4.63. Dalton would just have a stroke.
Yeah, that would be a pretty ugly number, wouldn't
He'd wind up in the hospital.
All right, so step 3, divide by the smallest, and 1.85 is definitely the smallest.
Okay, so I'm going to divide by 1.85 moles again, because that's my smallest.
Okay.
One of these I can do in my head. That's.
Hey, I can too. Oh, Mr. King.
Well, you're the one with the calculator.
I know, but that would have been fun.
2.502, 2.502, right? So we're going to round that to 2.5 because it seems close enough to 2.5. Now, are we done? Can I say N102.5?
No, this is one of those situations where we have to do the fourth step,
So
correct?
here's the beginning of the fourth step. I have to multiply both these numbers since it's a ratio, just so that I can get 2.5 to be a whole number.
By 2.
All right, by 2 is good.
Both of them.
Okay, so 2.5 times 2 gives me 5. 2 times 1 gives me 2.
Those look like good whole numbers.
These are nice whole numbers. And if I follow these 4 steps, I'll always get whole numbers.
Okay.
If I've done it right. If I haven't done it right, then I don't get whole numbers and I know I have to erase everything and start all
Yeah,
over.
these usually pretty much flow.
Yeah. Okay.
So dinitrogen pentoxide.
That is the answer.
Okay, now, Mr. Kane, I noticed that that's a molecular compound.
Yep. It turns out that ionic compounds, like we've talked about before, they're usually already reduced into empirical formulas.
Okay, so most of the empirical formula examples and problems will revolve around molecular compounds, carbon, nitrogen, oxygen, fluorine, etc. Okay.
Yep. So there's the answer.
Hey, we were right.
We were right.
We're so smart.
And the homework, not only say thank you to your teacher, but you might want to actually tell us what's wrong.
What's wrong with this video? Something's different.
Yep. All right. Besides the fact that there's no written homework.